and has nothing to do with PDEs anymore. I learned my analysis from the heat equation. So here's the heat equation again. If you define T of T, where the inputs of T of T are functions, the initial conditions, and the outputs are the solution to that PDE, that's just the semigroup is actually the solution to the PDE. Check it out. Property 1, T at 0 is U at 0, which is the initial condition. So T of phi is equal to phi. It satisfies the property of being the identity at T equals 0. Pretty cool? The next property has to do with invariance, because if I take T of T plus S and put T plus S in here, I get that's the same thing as U of T applied to this U of, so you get the same thing via translation. Got it, Ryan? What about this group property? They're the same by property of invariance. So you have that one too. The final property is that I need that limit to be continuous. I want it to be bounded linear operators. For every phi inside some set, remember that when I take this limit, I'm going to get a space right here where these phi's are going to belong to that space. That space has got to be where that limit actually exists. And it turns out that this space will become a Sobolev, what we call Sobolev space. So let me go one slide further. Right now, you can take B to be just uniformly continuous functions that are bounded. So we put the C0 to stand for uniformly continuous functions and B for bounded. So you can just say that that's where I'm going to restrict my initial conditions from. So the T of T is acting on functions, not like you had in Dr. Song's class. You were acting on n-dimensional vectors. Here they're at the entire input. And the space, the vector space you're working on is this one. This is your capital X. You're working on a vector space of functions. It is a vector space. It satisfies the A property over the field R. So it does all those A properties, and so this is a very fine vector space. And it has a norm. The uniform, what's called the uniform norm. That's the uniform norm. It's the maximum value or the suit, because you could actually level off, right? A bounded function, arc10 is an example of a bounded function that's uniformly continuous. So it doesn't necessarily need to have a maximum, so it goes to the suit. Example, you could take omega to be minus L to L, look familiar? And take phi of x to be sine x, perfectly, uniformly continuous, bounded function inside that omega. And I even know what that soup is. It's 1. So I can calculate its norm. And I think in real analysis you might have actually had this uniform norm and talked about it. All right, then don't tell anybody, because you should have actually had that in real analysis. So this guy, I mean, I think it's perfectly reasonable to give this in a real analysis class. I haven't taught it, but I think this is a reasonable problem to get to prove that this satisfies norm properties. Non-negative, because absolute value is non-negative. It satisfies that if this is 0, then the maximum is going to be 0. So I have the first property satisfied. It satisfies that scalar is scale up, got that one. Triangle inequality, well, the absolute value satisfies the triangle inequality. So it's a norm. So I thought I could give you just an easy one to calculate the norm of phi for two functions. So this is how I thought I could do it. And if you find them, I don't think this one would be too hard. You're just applying the definition of the norm in that particular Banach. And it is a Banach space, by the way. Now, there's other norms that you can apply on C0b, but usually it's not complete.
Now, when you say negative infinity to infinity, the whole extended grid line?
Well, what's this infinitesimal generator then going to be of this guy? Well, from ODEs, let's go back to where this is all coming from. Mike, is it too much?
Oh, no, I'm trying to figure out the question. Arc tanks would be one out of the spot.
Right.
The other one,
you had a... Right. So everything in life comes from this differential equation. This is the first one I probably showed you this semester. This is where we started. We're back to where we started. Well, the solution to that thing is x0 e to the at. We hope that a Calc 2 student can do that. They destroy our hopes sometimes, but I have a semigroup here. If I set T of T to be that solution, guess what? I've got the identity and the group property satisfied by the exponential. With laws of exponents. So if you ever teach Calc 2, you can say, today I'm going to teach you semigroups of linear operators. It is. And I also have that it maps, T at 0 maps is the identity map. Because when I plug T at 0 in there, I get identity and everything's unchanged. So what would the infinitesimal generator be for this guy? With that one, I can actually calculate by hand without using a uniform norm because I'm just working in R. It's just an absolute value. So if I do the absolute value on this guy, I'm really looking at the limit of this guy. That's the derivative evaluated at 0 of e to the at, which is A. Cool? So the infinitesimal generator, if this particular simple ODE is little a, the coefficient in front of the x. You can do the same thing for a matrix ODE, the same analysis I did right here for the matrix. So it turns out that in the case of the matrix, the infinitesimal generator is going to be the matrix A. And the solution is going to be e to the at with x0 out in front. So what about for the heat equation? Well, it turns out we can write the heat equation in this way. Instead of having it ut equals k Laplace u, I can say that the u's live in the world of C0b. So I'm taking the derivative on C0b, and the Laplace equation, the Laplace operator, can act on those functions, and that's my A, and my T of T is going to be the solution to this guy, which was just like the e to the ATs, and the infinitesimal generator will be A. Huh? Laplacian is the infinitesimal generator. The only problem you have is what the heck is the domain, because it's not right on the other ones. It was very clear. You take the limit always existed. I plug in 0, I get little a, so all the limit is fine. The limit is not fine here. The only catch is that this d of a is not entirely going to be uniformly continuous bounded functions. This is the intro to Sobolev spaces. This is why we introduced them. So actually, I can make this d of a. I can guarantee you that it exists on the particular d of a. Because now the problem with all the machinery you've built here is that these limits exist and are just fine in the world of the real numbers, but all of a sudden when you make your spaces really big, you're talking about an infinite dimensional space. R is a one-dimensional space. Rn is an n-dimensional space. You have all of linear algebra that you learned from Dr. Song works there. All of linear algebra doesn't work in the land of infinite dimensional spaces, and I think he might have shown you a little bit of that towards the end of the semester. Maybe not. He ended up with Graham Schmidt.
No, we are not.
Okay, so he worked in the world of finite dimensions. So now we're in an infinite dimensional space, so not everything works, and the one thing that doesn't work is the limits. Like just because you take a limit doesn't mean the limit has to exist. So when you look at this domain, it just doesn't turn out to be the original space that we started out with. So I'm going to take a few steps back so I can define for you what a Sobolev space is. I told you, it's a lot.